Swayam Prabha. Digital India. Educated India.
So we saw that for a lossy transmission line, the input impedance, suppose we have a transmission line. Okay. Now, because this is lossy, the propagation constant is the complex gamma, and say the characteristic impedance is 0, and this is shorted. So then we use the formula for a lossy transmission line, which is where this complex gamma is given like this. So now for a shorted line, then these two get cancelled. What we obtain is like this. Now, assuming that the losses are small, so we are assuming that the transmission line is lossy, but not that lossy. So if the losses are small, then we can make this approximation. Then Z in again, if this alpha L term is small, then this can be further approximated. So it should be an approximation sign here. As if this alpha L term is small, then this entire this term itself can be considered to be 0, and so then this becomes so this is a very simple form. It is like a R plus JX form actually. Okay. So this is just like any other, any other complex impedance. There's a, it's like two. It's like a series resistor. It's like a resistor connected in series with a reactance, capital X. So what we did was we reduced our lossy transmission line, low lossy of course. These are the parameters associated with that lossy transmission line, low loss transmission line. And this has been shown to be equivalent to this. So here we are using a box for this capital X because we don't know whether it's capacitive or inductive. Okay, that's right, it's a box. Okay, so coming back, once that we have established an equivalent series circuit for this lossy, low loss transmission line, let us try to find out the various Q factors. So to find out the Q factor of this resonator, which is a shorted low loss transmission line, and since we cannot determine whether X is inductive or capacitive, let's take help of that formula for unloaded Q, which is given like this. Now here, in order to compute in the formula that I had written earlier, I had written it like this, right? Omega r or omega 0. So as I said, omega r and omega 0, we are using it interchangeably. So, but then let's go back to the graph and see that the resonance, the series resonance happens at 2 omega 0, right? Isn't it? Either 0, which is a trivial solution, or 2 omega 0. So then, or basically for every even multiples of omega 0. So let us do it that way, that instead of writing it as omega r or omega 0, let's write it as 2n omega 0 or 2n omega, because omega r and omega 0 I have used it interchangeably. Now, so this then becomes equal to, now I use the formula for of omega as this formula, sorry, where Bp is the phase velocity. So then this simply becomes now x here is given by and r is equal to, so then this becomes equal to, and if I differentiate this equation with respect to beta, what I get is we have a number of cancellations. Now beta L, recall, can be written as so then when omega given by this expression, so beta L for omega equal to 2 and omega 0 will be equal to pi by 2, which becomes pi n. So then Qu equal to beta 0 on 2 alpha x square pi n, which is equal to beta 0 on 2 alpha. So here this so here this is the final expression that we get for Qu. Now this can also be further simplified as 2 pi upon lambda 0 upon 2 alpha, which is equal to pi upon alpha into lambda 0. Okay. So one advantage of this low loss shorted or open transmission line based resonators is that we can obtain very high values of Qu. Uh, for example, we can obtain Qu equal to 4000 for alpha equal to now a similar derivation I have given in the notes for open line resonator. So a transmission line which is open or an open stub low loss resonator. Please go through it. The next topic that I want to cover is what is known as a capacitively coupled open line resonator. So capacitively coupled open line resonators. So the construction is like this. This is the feed line. So this is the input having characteristic impedance Z0. There is a gap and then an open line. This is a open circuit resonator or simply a open stub. So this gap, it creates a capacitance between the two, between the feed line and the open circuit resonator. Equivalent circuit model of this is like this. So there is a transmission line, there is a capacitor, and then followed by this open circuit resonator. So the characteristic impedance of that open circuit resonator is Z1. So now let's say that omega 0 is the resonant frequency of the open circuit resonator only, and omega r is the resonant frequency of the overall system. So let us say we are considering series resonance. So now if we want to compute the reactance that is seen from this end, then we can write that x in is equal to minus 1 upon omega rc minus z1 part of beta rl. Okay, so and that at the resonant frequency is equal to 0. So here note this omega r, that is the resonant frequency of entire system. So it is not the resonant frequency of only this open circuit resonator, or so it is of the complete system, okay, this whole system. So at for series resonance, then this equation has to be satisfied. So I can also write just for completeness, Z in is equal to J of X. Okay. So how do we obtain the resonant frequency? Once again, I would like to repeat. So omega 0 is the resonant frequency of only the open circuit resonator, and omega r is the resonant frequency of the entire system. So to do this, what we can, to find the resonant frequency, we can start the way we had obtained the resonant frequency for the shorted stub. So this is imaginary part of Z in the function of omega. So our diagram of our circuit is like this. Okay. Now in terms of L, so first let me draw the circuit, draw the characteristics. Something like a tan curve, and this value is and if we also plot the, so this is, these characteristics are purely for the open circuit resonator, and then if we also plot the the characteristics of just the capacitor, it will be something like this. Okay. So what do we see, that previously the resonant frequency, it was at, for the open circuits resonator, the resonant frequency was at omega 0, but now with with this capacitor, gap coupled capacitor present, the new resonant frequency is here, this one. It's the intersection of the two lines, or it's also here. Okay. Now, why, you might ask, why is this intersection point frequency corresponding to this intersection point the resonant frequency? Because if we go back to this equation, so x in equal to 0 implies 1 by omega rc will be equal to minus z1 quart of beta rl. So this blue line is nothing but minus z1 quart of beta rl, and this purple line, this line is 1 upon omega c, just beta l. Okay, and that's why the intersection point, this point, and the frequency corresponding to it corresponds to omega r. So here also I should give so omega. So that's how we get so the point where these two frequency where these two are equal, which is this one and this one, omega, is the frequency of resonance of the whole system. Okay, so now how do we find out the Q factor of this resonator? First of all, when I say Q factor, which Q factor is the most appropriate? Note that here all the lines, all the transmission lines are considered to be lossless. So this is entirely a lossless system. Our resonator part is this. Now this feed is assumed, this is where we provide the input signal. So this feed can be assumed to be infinitely long. If this is infinitely long, then the load for this resonator, the external load for this resonator will simply be equal to Z0. So that capital R in the Q factor formula is nothing but Z0. And also, since the resonator itself is lossless, QU will be infinite. So the only Q that is finite is QE, and recall it is given by omega R upon 2R d of x in d of omega at omega R. Here QE is equal to QL because since QU is equal to infinite, being lossless, the resonator itself being lossless. So here the load again is provided by the feed line itself. The characteristic impedance of this infinitely long feed line can be considered as the load. Okay, so now let us try to evaluate that. Okay. In fact, I leave it as an exercise for you to evaluate this complete expression. Just write it down once again. This beta L can also be written as omega L upon Vp, and thereby this relation gives the omega dependence of this term. And then I leave it as an exercise for you to prove that this QE will be equal to now this derivation is given in the book by Rizzi. So you can refer that also, or you can try to do it yourself. Try to prove this whole expression, whole system. Try to prove it. Now, what is the use of this gap coupled resonator? Since there is a gap, the resistive part is very low. The resistive part is very high, and the losses are quite less. And because the losses are quite less, very high Q factors can be achieved, even higher than that of the open circuited resonator or the shorted stub resonator. Since in both those two structures, the open stub and the short stub, there is a direct electrical connection, and that causes more losses. But for this gap coupled resonator, the losses are quite less, hence very high Q factors can be achieved. So with that, we come to an end to this part, this resonators. In the next part, we'll be covering the actual design of narrowband filters using these resonators. Thank you. Hello, welcome to part 3 of lecture 14. So in the previous two parts, we had covered the basics of a resonator. And in this part, we are going to cover the actual narrowband filter design using a resonator. So let me share my screen. The first thing that we have to understand, in order to design a narrowband filters, two types of narrowband filters exist. Now, to achieve a band stop filter, the general rule is so what do I mean by that? Suppose we have a circuit like this. So this is a series resonator, right? But it is an shunt. Shunt because this is parallel, isn't it? Connected parallel. So this is a band stop filter. This is the input, this is the output. Similarly, if I have, say, this circuit, now here, this one is a shunt resonator in series. It is a shunt resonator, but it is connected in series. Hence, this is also a band stop. For band pass, the converse. What is the converse? Series resonator in series or shunt resonator in shunt. So let us see, say this circuit. This is a series resonator connected in series, or say we have a circuit like this. This is a shunt resonator in shunt. So both these are examples of band pass. So this is the first thing that we have to understand, okay? That to construct a narrowband filter, there are two types of narrowband filters. One is a band pass and band stop. Note that we are not talking about low pass or high pass filters. Okay, so narrowband starts with band pass. So, okay, now what are the characteristics of a band pass filter? Let us go back to this parameter S21 square, which we recall where was used while I was discussing amplifiers. And I told that time that if the input and outputs are matched, then this quantity represents the total gain. Now, filters that we are discussing in this lecture are the passive type. The passive, if it is passive, then S21 square will be lesser or equal to 1. Okay, and we define a quantity called insertion loss L, given by this parameter. Okay, now because this quantity is lesser or equal to 1, hence insertion loss for the passive narrowband filters that we are discussing, L will be greater or equal to 1. Okay, and if we plot this insertion loss versus frequency, okay, then band pass, so this is L, actually it is Li, Li. Sometimes Li is also expressed in dB. So Li is also equal to minus 20 log 10. Okay, so for a band pass filter, in the pass band, the loss will be low, and in the stop band, the pass loss will be high. So they might have characteristics like this. This is my F0 or resonant frequency. So this is for band pass. For a band stop, the reverse. For a band stop, it will be something like this. Okay. So then now this gap, let us then start our first band stop filter based on what we already know now. So we have seen that a gap coupled resonator can provide series resonance. So suppose we have a okay, so this is my port 1. This is a Z0 line, and say I add my gap coupled open circuit resonator. So this part we had studied in the previous video. So this is an open circuit resonator, characteristic impedance Z1, lambda by 2, so that why lambda by 2, so that it can provide series resonance. Okay, so this is port 1, this is port 2, and here is my band stop filter. Why again, why this is band stop? Because this is my series resonator when the length is lambda by 2, and it is connected in shunt. So from the principle that I just mentioned, it acts like a band stop filter. But then how to find out the insertion loss? So the equivalent circuit model for this is something like this. How do I find out the insertion loss for this band stop filter? So to do that, again, let's take help of ABCD parameters. The first thing we note here is that this whole part is in shunt. Okay, so now suppose I calculate the input impedance offered by this segment. Now this is actually two parts. One is a capacitor and the other is a transmission line part. Okay, so in that case, my Z of omega, the value for Z of omega will be given by the insertion loss is the ABCD parameters for just this part in shunt is given by and Li is given by, so this it becomes equal to so the insertion loss is given by this formula, and we also know the formula for S11, S11 magnitude given by, so this turns out to be Now, at resonance, at series resonance, Z of omega becomes equal to 0. So then S11 becomes equal to 1, and Li tends to infinity. So what it means is that at resonance, the input reflection coefficient becomes 1 and the insertion loss is infinite. That is, S21 is 0, S21 magnitude, which is what a band stop filter is, isn't it? That at resonance, it will stop the signal from flowing. Now, we can try to find out the Q factor of this filter. So there is a slight difference between finding out the Q factor of a resonator and the Q factor of a filter. Let me show by an example. So our gap coupled band stop filter, the circuit is like this. This is my gap coupled open circuit, which has an input impedance Z omega, right? Now we can, so let me just, so this is open, this terminal and this terminal. So we can obtain an equivalent circuit for this. It will be something like this. So this shunt resonator, okay, and be modeled for series resonance. This this resonator, which is connected in shunt, can be modeled as a series resonator in shunt near the resonance frequency, like this. And this whole thing is as a impedance Z of omega. So this thing, okay, the same way. Now, so let me, this port 1, this is port 2. So we know that Z of omega is equal to R plus J omega L minus 1 by omega C. This is the input impedance of this series resonator Z of omega in terms of this circuit parameters. And we also saw that this can be approximated, not approximated, this can be written as okay. Now, what is the value of this capital R? We saw from analysis of low loss transmission line earlier in the earlier part, in part 2 of lecture 14, that this can be approximated as okay, and QU So that so if I want to find out the QE, how do I find it the QE? So to find out the QE, what I do is I short this generator and see what is the external loading. Okay, so if I short that generator, my circuit will become like this. So this comes here, this comes here, and this series resonator is this part. Okay, then the color. Okay, now assuming that this resistance value is small, this can be further simplified as, so we have these two impedances are in shunt with respect to this resonator. I can simply reduce them. Okay, so this is again my resonator. Okay, so for this resonator, the external load is this one. So then QE becomes equal to omega R L upon Z0 upon 2. Okay, and Q unloaded becomes equal to omega RL upon R. So QU upon QE becomes equal to Z0 upon 2 on R. Okay, and we saw that this R, this is equal to R value is an approximate sign, alpha L Z0. So this becomes equal to 1 upon 2 alpha L. Okay, so this is the ratio of QEU upon QE. Now, here I have shown what is the value of QE when a series resonator is connected in shunt. Try to obtain the expression for QE for these cases. So, series resonator in series, shunt resonator in shunt. Okay. Now this one was what? This one was okay. So I have shown that when a series resonator is in shunt, the QE value is given like this. The challenge is to find out what should this R for these various cases be. For these various cases, the numerator will remain the same. So try to derive that, and I leave it as an exercise for you. Now, there are some general formulae. There is a general formulae relating this QU, QL, epsilon F, and the insertion loss.